MCAT 2017 Cram, Physical Foundations of Behavior. Passage 1, A Physical Model of Human Sitting. As you view the reading of the passage, you'll notice a few highlighted snippets of text. What I want you to do is garner meaning from the selection in order to answer the 5 questions that follow. The passage really isn't that bad. It's mostly going to be used as a reference, and neither are the questions. So good luck and happy reading. Paragraph 1. A comfortable sitting position for a patient leaning back on a stool, figure 1a, requires the weight and torque of the upper half of the body to exactly counterbalance the weight and torque of the lower half of the body. The hips of the patient serve as a pivot point for a simple balance, but they also allow the patient to adjust the angle theta of his posture. So he can lean forward or he can lean back. Okay? So theta, so that he can maintain his balance. Paragraph 2. The patient can be modeled as 2 uniform rods with H, the length from the top of the head to the hips, and L, the length from the hips to the feet, by changing the angle between the torso and the legs. The patient can adjust his balance. The mass of the upper half of the body is M sub H, and the distance from the center of mass from the hips is given by H over 2. The weight of the lower half of the body is given by M sub L, centered at a position L over 2 below the hips. Okay? Paragraph 3. Suppose that the patient fails to maintain his balance and tilts off the stool and falls towards the ground. As he falls, his hips remain in contact with the stool without sliding, such that the motion of his head traces a circular arc around the point where his hips make contact with the stool. Figure 1b as shown here. The patient can avoid hitting the ground only if he adjusts the positions of his legs to counterbalance the torso. Figure 1a, the posture of a leaning man sitting balanced on a stool. Don't try this at home. Figure 1b. After losing balance, the man's torso traces a circular arc, centered at the point at which his hips contact the stool seat. Which of the following definitions accurately describes the sitting position in figure 1a? Is it A, anti-equilibrium, B, non-equilibrium, C, stable equilibrium, or D, unstable equilibrium? I'll give you a moment to think. Notice you don't need the passage for this question. This is a standalone question that requires you to have outside knowledge of the correct terminology. All right. Okay, so the man needs to actively use his muscles to regain his posture if this angle theta is disturbed. In stable equilibrium, the minimum potential energy is at the equilibrium point. The patient, when set off, tends toward a position other than the equilibrium point. Basically, this is not a widely used term in physics, but this is unstable equilibrium. Okay? Yeah, because he's not stable. He's not stationary. Okay? And the other terms just don't apply. Which of the following relations accurately describes the equilibrated sitting position shown in figure 1a? M sub L times L is equivalent to M sub H times H. M sub L times L over 2 is equivalent to M sub H times H over 2, the cosine of theta. M sub L times L is equivalent to M sub H times H, the sine of theta, or M sub L times L over 2, times L squared equals M sub H times H squared. I'll give you a moment to think. This only requires minimum knowledge from the passage where you incorporate M sub L and M sub H and H. Well, actually, yeah, this is the most important question that the passage needs. It's really not that bad if you know the scientific concept that they're wanting to express here. All right. Okay, so in order to remain balanced, the torque is what they're looking for, on one half of the body must counterbalance the torque acting on the other half of the body, okay? So the torque is proportional to the force of gravity multiplied by the perpendicular distance from the pivot, okay, point at which it acts. So here goes the pivot point, and this is the vertical component of the force of gravity acting, at this point. The torque is the product of the weight. So torque is the product of the force applied to the lever arm, the lever rod here being the patient's upper body, at whatever position it's being applied on that lever arm. And here, the gravity is acting obviously at the center of gravity, okay? So that's the position, or H over 2 as we're told in the passage. So again, the torque is the product of the weight of the patient's torso and the distance his center of mass lies from the pivot point. So simply gravity, he's not perfectly straight, so we're going to take the component perpendicular to his axis, acting at the center of gravity, okay? So the perpendicular distance from the pivot point at which gravity acts on the torso is given by H over 2, again, where his center of mass is located. So the torque is balanced when M sub L times L over 2 equals M sub H times H over 2, the cosine of theta. And remember, basically, this is a simplified version of the torque. What they did was they got rid of g, the acceleration due to gravity on both sides, because the force due to gravity is mass times acceleration. So it would be M sub L. The weight of his lower half would have to equal M sub H, the weight of the upper half of the body, times the position on the lever arm where the force is acting, and they're acting at the centers of gravities on both sides. That's why the distance of the lever arm is L over 2 and H over 2. And for H over 2, it's times the cosine of theta because he's not perfectly straight as he is here, So we have to take the vertical component of gravity, and in this case, it's going to be modified by the cosine of theta, because remember, if you were to make a triangle here and kind of rotate this angle theta corresponds to this angle, and it's the adjacent angle modifies the component or the side of the triangle by a factor of cosine theta, okay, not sine, so don't choose this. All right. In which approximate direction is the net force on the man's torso oriented as he falls in figure 1b? Is it A, upwards from the stool? Is it B, the direction varies as the man falls? Is it C, along the direction of the torso towards the hips? Is it D, downwards toward the ground. All right, so I'll give you a moment to think. Okay, because the man traces a circular trajectory, the stool exerts a frictional force perpendicular to gravity that prevents him from sliding. This frictional force needs to be added to the contributions of the gravitational force to determine the net resultant force. That's why for some people who thought the answer was downwards towards the ground, it's wrong, because you also have to consider the friction of the what looks like a wooden stool rubbing on his bum to keep him from falling. So with that said, because the force due to gravity has a constant direction, the centripetal force points towards the stool, and the sum of the forces changes. What determines the distance the center of mass lies from the pivot point? Okay, so what determines this distance from the center of mass? Is it A, the weight of the stool? Is it B, the angular distance the patient has fallen? Is it C, the height of the patient? Or is it D, the height of the stool? I'll give you a moment to think. And if you don't know what to think, just sit tight. The answer is coming up. Okay, so in order to answer this question and better exemplify it, let's use this scenario. The maximum torque experienced by this patient when falling is going to occur when the torso is parallel to the ground, basically when this dude is flat on his back. Okay, and you have to remember that the torque is the product of the weight or the force due to gravity applied to the position in the patient's torso where the center of mass is located. And we're told in the passage that the distance of the center of mass from the pivot point of the upper body is basically h over 2, okay? This may not really be what it is in reality, but it's a very good approximation and a good number to use for demonstrative purposes, or variable rather, because there's no numerical value given. So ultimately, what you can see here is that the distance the center of mass lies from the pivot point is determined by the height of the patient. Okay? All right. When the individual is sitting stationary in figure 1a, the net force acting on the individual points in which direction? Is it going to be A, the direction depends on theta, B, upwards from the stool, C, downwards towards the ground, or D, the net force is 0? I'll give you a moment to think. Okay, so sitting the individual is motionless and basically not accelerating. The upwards force exerted by the stool cancels the downward force exerted by the weight of the individual. So the net force is basically going to be 0. Okay? All right.